At the point when the $10 billion gadget prepared its infrared vision on the exoplanet K2-18b, 120 light-years away, it identified dimethyl sulfide, a sulfur compound that, on Earth, is created solely by life forms. Does this imply that the matter is settled? Might we at last answer the oldest question of humanity, whether we are truly alone in the universe, with a clear no? Well, that is the essence of the cosmic discussion. While one side of the specialists is already popping the champagne corks, the opposite side is calling for somewhat more patience and pointing out that even the capacities of the most impressive space telescope of all time are limited. Hand on heart, in most people's daily routines, dimethyl sulfide, or DMS for short, likely plays no significant role. In fact, many people have likely never even heard of this specific synthetic compound, although they have likely experienced it at one time or another. Exhaustively, DMS is formed by minuscule green algae, the phytoplankton, which float in the highest layers of the sea, and it's responsible for the familiar smell that we notice when we are at the seaside. Apart from its sniffing properties, DMS also has another significant characteristic. Up until this point, we only know of natural sources for this sulfur compound, and where the production of a substance needs the support of organisms, it's understandable that DMS plays a very special role in the search for extraterrestrial life. This is particularly relevant at the calls of celebration that came from the lips of the Cambridge cosmologists in September 2023. After all, the James Webb Telescope had identified nothing less than this potential biosignature on the exoplanet K2-18b. The overwhelmed pioneer, Nico Matusin, then let the press know that he and his partners were totally stunned by their readings. No surprise, because after all, the presence of DMS in the immensity of space is nothing short of a serious sign of extraterrestrial life. What initially came as a shock to the scientists soon turned into euphoric reporting, which inelegantly raised the James Webb Telescope to the key to the grandiose look for life. But is the matter, in fact, as obvious as it seems? If the corresponding atom on Earth is only produced by living things, and we then find it on an alien body, why hasn't NASA officially reported that our tiny neighbors are thriving on K2-18b? Well, that's because, as so often, the unseen details are the main problem. But essentially, the circumstances in the case of K2-18b are anything but terrible. It is a water world, a sanctuary for life, located around 120 light-years from us in the constellation Leo. The planet is under the astonishing assumption of being a heme planet. In other words, a planet whose surface is totally covered with water and can therefore support life. While K2-18b was added to the star charts in 2015 with the help of the Kepler Space Telescope, it orbits its central star, the red dwarf K2-18, inside the habitable zone. This zone describes the distance range at which a planet should be found relative to its host star for water to exist there in a forever liquid state. Of course, the cool, wet element is considered one of the key points of support for the development of life, like that on Earth. And despite K2-18b being fundamentally cooler than the Sun, its planetary companion receives roughly the same amount of radiation as our Earth, thanks to the given star system. Most importantly, K2-18b is just 0.14 astronomical units away from its parent star, meaning it requires only 33 days for a complete orbit. Furthermore, the key component in this life conversation also contains the entries methane and carbon dioxide, and thus, two further pointers suggest that we may actually be dealing with a habitable planet here. If this is truly the case, it would be a vast curiosity since, up to this point, these exotic water worlds have only existed on paper. While the identification of methane and carbon dioxide, in combination with the absence of ammonia, suggests that K2-18b is a Neptune-like planet covered by liquid water, the identified substances also present a puzzling confusion. They make it even more challenging to interpret the DMS data accurately. The secret of the biosignature, on a basic level, the DMS signal was anything but pronounced in the collected datasets, and it only revealed itself when the data was analyzed in a particular way. The matter was not made any less complicated by the fact that the DMS signature identified by Webb's near-infrared spectrometer, an IR-SPEC, appeared in a spectral line at a frequency of 3.4 microns, which coincidentally overlapped with methane. And that is precisely the core of the matter, because the researchers believe that distinguishing DMS from methane is essentially beyond the capabilities of an IR-SPEC. But does this also imply that Webb's abilities have already been fully depleted, and that we cannot uncover the true background to the DMS question? Fortunately, no. The scientists also emphasize that definitive evidence is theoretically possible. After all, DMS and its breakdown products also produce a signature in the mid-infrared range, somewhere between 9 and 13 microns. Conveniently, this is the very range in which Webb's mid-infrared instrument, MIRI, works. While the main NASA declarations still discuss a potential detection of the molecule dimethyl sulfide in this context, the Cambridge researchers finally wanted to know more. Thus, it turned out again that the astronomers used Webb's sharp infrared vision to get to the bottom of the mystery surrounding the alleged biosignature. During this, the specialists allowed 8 hours for the designated search for DMS, 1 to 2 days afterward. The research team would then receive the data and begin with the assessment. Anyway, it's in the nature of things that such data assessment is, to say the least, relentless, or rather, it takes months before it's fully completed. The good news, however, is that the scientists have already been working on the investigation for several months, and so it shouldn't take much longer before the latest findings regarding the presence of DMS on K2-18b are published. When will we detect DMS? Luckily, the rest of the cosmic world isn't condemned to just waiting and wasting time. In the meantime, after all, they can also approach the DMS question from a theoretical perspective. In other words, with the help of their models, scientists can check when we will be able to detect the presence of DMS on K2-18b. And that's exactly what the team led by Sean Manai of the University of California, Riverside, has now done in detail. The scientists recreated K2-18b and its possible biochemistry using several models, simulating the planet covering sea and air. The researchers then wanted to test how much DMS our extraterrestrial microbial neighbors would need to produce for it to accumulate in the air, so much that we could detect it, and how quickly it would be broken down again due to radiation. The study concluded with the exciting result that the ongoing data assessment by the colleagues is not in vain. Theoretically, it is possible that biogenic sulfur gases on hydrogen-rich sea worlds like K2-18b could accumulate to detectable concentrations. But, as so often, the big but follows. This only applies if the organisms of K2-18b are real workhorses. In fact, extraterrestrial DMS production would need to exceed that on Earth by a factor of 20 for us to be able to register it with our instruments. This is for the simple reason that the majority of DMS is broken down promptly by photochemical decay due to solar radiation. In the case of potentially higher concentrations, which are very possible for speculative exoplanets, a natural protective effect would arise that would halt DMS loss. In this manner, its breakdown products, such as dimethyl sulfide and methane, form a kind of protective shield around the lower atmospheric regions, which are thus shielded from further DMS degradation. However, only the future will tell how much this scenario corresponds to reality. What is already clear, however, is that the definitive confirmation of DMS would be no less than a remarkable achievement in the history of space exploration. And while the team at Cambridge is currently busy assessing the new datasets, as mentioned above, the lead researcher underscores that even one direct detection would be enough to change the entire history of science. No wonder. After all, humanity has been pondering for centuries whether there are other living things out there, and eventually, a single model would be enough to end the centuries of speculation. At the same time, whether the extraterrestrial life breakthrough will be named K2-18b can't be said with absolute certainty right now. But we already know of no other candidate that opens up such a promising lead for us in the search for life in space. And the path of your video search currently leads you directly to the membership button. Go ahead and click subscribe so you never miss another video from us again. We'll see you soon.